Okay, so we've talked about acceleration, velocity, and distance last time. So now we're going to do work. Do you know we hadn't done any work in this class yet? Get it? I got jokes. All right. So what is work? Work is a force applied over a distance. That's the meaning of work. You apply force to move something over a distance, okay? So then the formula, the basic formula is force times distance. So the simple case is if you have a constant force over a straight line distance, then you can just use this formula and then we'd be done talking about the subject. But there's more complicated situations, and that's what, we're in the big leagues now, and so we can do harder stuff than that. All right, so the units always follow right along with whatever the formula is. If the formula is force times distance, then the units will be the force units times distance units. So force is in newtons in metric, and meters is standard metric distance, so Newton meters. This is not minus, this is newtons times meters. And 1 Newton meter is a joule. So a joule is a shorthand for the work that you would do applying 1 Newton to push something 1 meter. That's a 1 joule. It's a Newton meter. Okay? So an immense force applied over a distance of 0 meters yields 0 joules of work. So here's our bright young student here at Midvale School for the Gifted. And he's pushing really hard on this door, right? So how much work is he doing? A lot of work? 0. Why 0? Because no distance, right? So as long as that door holds him back, he can push for as long as he wants, as hard as he wants. He will accomplish 0 work. Has to be over a distance. Now, if he can get that door moving down the hallway, now he's doing work, okay? Now he's doing work. All right, so chair over here. I'm bright too. What about me? Am I doing work?
Yeah.
Yes, I'm doing work, right? Because I'm putting a force on this to move it over a distance. So what happens to the work that I do as I push it? So before I start, my work is 0. So now what's happening to the amount of work that I've accomplished? It's increasing, right? So at any given moment, I've done a certain amount of work, and that amount of work is increasing as I go. So that's the idea of accumulation, right? So this is a perfect example of another quantity that accumulates, right? Accumulates. And so we can write an accumulation of work. And so we're always thinking about how much work has been accomplished at the current moment, right? Well, that's a work function, right? That's a work function. And so we can write a net accumulation of work function to track how much accomplished work has been done so far, right? Okay, so it gets more complicated when the force varies, right? So if the force is varying while you're applying it, if it's increasing, decreasing, then that makes a more complicated situation. And then if the distance varies, like if it's a curved path or up and down or something like this. So these things don't allow you to just easily just do a force value times a distance value and be done, right? So this is where it gets more complicated, but we have the tools to handle situations like this, to create a accomplished work function or an accumulation of work function. So let's look at an example called the pushy ant. The ant is going to push a seed. Back off a little bit, yeah, okay. So the ant pushes the seed along a path like this. It's a very smart ant. Knows this curve here, and it's pushing it along this path. And so we want to know how much work will the ant have accomplished at each distance along the path. So at any given point along here, how much accomplished work has the ant done, which will just keep increasing as he goes. So if we want to write a net accumulation of work or an accomplished work function, what do we need? Yeah.
Also, I think we need the arc length to get the distance.
Okay, yes, so that's going to be all involved. But just in general, if we have the rate of change of work, we can really quickly write down the accumulation of work function, right? We've been saying it almost every day in class, right? So this is what we're after, okay? And so in order to find that rate of change, we can kind of theoretically think about what would dW be. So this is like a little variable amount of work somewhere along the way. So if work is force times distance, then what's a little bit of work? If work is force times distance, then what's a little bit of work along the way? Yeah.
Force times a little bit of distance.
Yeah, right. So it's going to be the force at any given moment times the little bit of distance that you go. So let's write that down. All right, so the question is, what is a little bit of distance that the ant is going? All right, so eventually here we're going to, all right, let's go and do it right now. So we're going to put that path in the xy plane and model it with this curve. And so what is a little bit of distance that the ant goes? How would we symbolize that if we stick with the conventions we've been using? What would be a little bit of distance for the ant along the way? Yes, sir? dx. What do you think? Is that a little bit of distance that the ant goes? dx. Okay, someone's offered ds. So now dx and ds have been offered. What is a little bit of distance that the ant goes? Is it one of those or something else? dx, ds, or something? What do you think? You think what?
Ds.
ds. It's ds. That's right. We know that, right? ds is a little bit of arc length, right? A little bit of arc length. And so if we want the force, if the work that the ant is doing as he moves along the path, then that's going to be, along the path is going to be a little bit of arc length ds. Okay? But notice we want to write this rate function in terms of what? And eventually at the end, not in terms of how far the ant has gone, but as a function of the x, the horizontal position of the ant, right? So as the ant goes on this path, he'll always have a horizontal position. Okay, and that horizontal position is x. And so how can we, so right now this is kind of like in terms of s. We need to get this little bit of work in terms of x, but still for the work done along the path. Yes, sir?
The force times the integral from wherever you're starting to wherever you're ending.
So this isn't all of s, right? So that you're thinking all of s. And that's okay. So you're thinking like all the s up to the current point. But this is just, yeah, so just a little, the ds. Yeah, so you're just thinking s, and that's good. So a lot of you are saying it. So, and actually we know the force. What is the force? 0.3 or 0.3. So, yeah.
We would do square root of 1 plus
Square root of, right?
r sub w of x squared.
The rate of f, yes, the rate of f, yeah. Yeah, yeah. Is that it? Is that ds? It's not quite ds yet. ds was this thing, and then also dx. That's what we derived as ds, right? A little bit of arc length. So in effect, what this square root does is it it transforms from a little bit of arc length to x coordinate, right? So this is like a transformation from along the arc to the x-coordinate. But this little bit of work will still, it still is the amount of work along the arc. It's a little bit of work along the arc. It's just now kind of translated into being in terms of the x-coordinate rather than s. Okay, so if dw is 0.03 times the square root times dx, then what's the rate? So looking at what we just wrote, we know what the rate of change is. What is given that right there? What's the rate of change? Somebody please know this. Dylan knows. Anybody else? If we have an expression like this, dw equals dx, where the rate is in there. Yeah.
Is it the 0.03 times the arc length ds? Is that part not including the dx?
Okay, so the dx includes the ds, but what you said, yeah, so it's the not including the dx, this much.
Yeah.
Yep.
Yeah.
This is the rate because why is this the rate?
Y equals mdx.
dy equals mdx, right? So whatever the m is, so we did this when we did the volume problems, right? This is how we derived the rate of change when the height was growing versus when the radius was growing. We made the formula look like this so that we knew that that multiplier on dx, that was the rate of change, right there. Because dy equals m dx, so there's our dx. So 0.03 times square root 1 plus x squared. So now this square root is unitless. Like I said before, all it does is kind of does a transformation from s to x. All right, so this is a unitless quantity. It's just like a geometric transformation from arc length to horizontal position. So what is this then? If this is unitless, and this is, what was this again? Newtons. So what, the whole thing then is what quantity? What kind of quantity is it? Newtons, right? Which is force. So the rate of change of work is force. Because that's a force quantity right there. It's that constant force along the path translated into horizontal position. But the big takeaway here is that the rate of change of work is force. The units of that is newtons. Okay, so we're ready to write or start setting up. We got all the groundwork laid to write a work accumulation function for the ant along this path. So think about, if you have GC, you could start typing, or if in your notes, you could write down what will I type into GC so that I can have and graph a work accumulation function for the ant as he pushes the seed along. So I've got these already put in. I've got the path, and I've got, we're going to have a new force coming up, so I call this one F1. That's 0.03. Okay, so what would I put in next? My goal is to write the net accumulation of work function for this ant. What would I write next? What would the next line be? Yes, sir? So I'm going to call this 1. This is the first work function. We're going to do another one later. I'm going to stop you right there. So this is absolutely valid. We could go right to the work function. But I want to do an intermediate step. Yeah, so like I said, this is, you could put in where that question mark is and have it perfectly right, or we can do an intermediate step. And what was that? Remember? So to make that work function like almost like nothing to do at all. So the last thing to do here is fill in that question mark. So instead I could define, I know that Nick knows. Yes, sir?
Define the rate of change.
Yeah, can you do it?
So it's RW of X.
We'll call it rate 1 of X. Yes, but it's of W, that's right.
It's 0.03 times
And I'm going to use F1 just because I already defined it. But yes, 0.03.
times root of 1 plus f of x, or the derivative of f of x.
So derivative of F X and all of that. How's it look? Is that what we said? Okay, any questions? And so this is what you were going to do, right? You were going to put that in there. So now what can we put in instead? Right. Okay, little f. Open or closed form expression? Little f. What about big F1? Closed. Okay, what about the rate function? Closed, right? And then what about our work function? Open. Okay. So before we graph it, so if you are filling this in on GC, don't graph it yet, and we're going to talk about like try to predict what this will be like, understanding what work is like. So I'll turn it off first, and then we'll say, how do I graph it? What do I say? Y equals W1. And I want to graph starting from 0 and go from 0 to 3. So before I turn that on, let's kind of predict what this thing will look like. What are going to be some characteristics of this accomplished work graph of if the ant is pushing, starting at 0, is pushing the seed along this curve. What do you think? What's one characteristic we're going to expect from this graph? Yeah, tell me. Always increasing?
Yep.
Ever decreasing? So like, what about here at the beginning when the ant is below the x-axis?
That would be
Negative work? Okay, but we're talking about work, so what's the ant doing? The ant's pushing the seed along this path. Will that make negative work? Yeah, so for the ant is always full steam ahead. Even though it's staying on a curved path, it's always pushing straight ahead. And so can we conclude that even no matter what direction in the plane that ant is going, that the work is always increasing? Yeah. So that was the right conclusion. This work is going to go up and up and up. What other can we say about the graph? Can we predict about the graph? Where is this graph going to start? At x equals 0, is it going to be y equals 0 too? Okay, so at x equals 0, no work has been accomplished yet. So it's going to start at 0, 0. It's always going to increase. And then let's be a little more specific about what that might look like. Straight line, sloping curve one way, like concave up, concave down, something else. We'll have this general shape? No, because this goes down, right? So we know it's going to increase. So the question is, how do we expect it to increase? What's that? Linear? Flip linearly? So look at what about the amount of work that the ant does from 0 to 0.3 versus from 0.3 to 0.6? Can you compare those? You see how much work the ant would do from 0 to 0.3 versus from 0.3 to 0.6? When is it doing more? Why does it do more work from 0 to 0.3? Yeah, because in getting from x from 0 to 0.3, it covers a lot of ground, right? But then from 0.3 to 0.6, relatively a lot less ground. Do you see that? I know it's low on the screen, and that's better. So between 0 and 0.3, it's going down and all the way up like here. But between 0.3 and 0.6, it pushes it this far. So what would that mean for the accomplished work graph? Yeah, nice. Right, exactly. So we expect it to go up faster, have a higher rate of accomplished work. Here, where there's more distance per x, right? And then through here, yeah, it'll still be going up. It'll always be going up, but at a lower rate, right? So it'll be flattened out. And then again between 0.7 and all the way up to here, like to 1.3 or something. We expect a higher rate of work because as x changes, it's more distance is being covered, right? So then what will that look like then for the graph? Yeah.
Why didn't you type like just W1 from 0 to 3 instead of from 0 to x and then?
Why do I want, this is a huge, very important question. Why do I want W1 from 0 to x? I want to know what the work is at any value of x, right? I want the work function, meaning I want to choose any x coordinate that the ant has made it to and know what that corresponding work is.
All right, so 0 to 3 will give you this number, right?
If I put 0 to 3 here, does that say put a 3 here?
Oh, it's going to be a number.
Yeah, that'll be a number, and it'll just graph a horizontal line at that number. Yeah. Okay. Cool. All right, so it's going to go up linearly. A big sweeping up curve like this. A big sweeping down curve like this. Yeah, it's going to be like it's going to wiggle, right? It's going to wiggle based on the current rate of work being accomplished. All right, so notice, was this an open form or closed form expression? Open. Did it graph it pretty fast? Right? Yeah, so we said the open form expressions don't lend themselves very well to calculating fast, but it was able to do this pretty fast. Okay, compared to what? Remember the acceleration on Wednesday? Why did it take so long for the acceleration? Do you remember? Yeah. Yeah, it was like a double layer of open form, right? The open form expression was being generated based on another open form expression. Okay, so the technology is really good that it can do an open form, just a single open form expression. It can graph it fast. Okay, it's when you start layering it that it has to work really hard. So there's questions, yeah.
Function be open form if it doesn't have an arrow in it?
Yeah, there are other types of, but this is just the ones that, yeah, there are other types of open form expressions besides integrals, yes. Like the limit definition of a derivative. That's open form. Remember that? Calc 1? Why? Because that expresses meaning, right? It expresses meaning. But the fact that it's this limit of this ratio, it's not something that will rapid fire results quickly for you. But it expresses the meaning of what derivative is, that it's rate of change at every moment. Rate of change at every moment, letting your moments get very small. So that's another example. Okay, so I'm going to pick a point here. As always, what is a graph? It's a collection of points. So you're looking at a zillion points there that represents this relationship between two quantities. So I want you to interpret the meaning of that point. So this ordered pair, two values, what does it tell us in the ant scenario? Okay? Get a partner? Talk about that. Let's hear what somebody new. Is there a young lady? Someone here? Lots of guys so far. So is there a young lady, someone new, who would like to tell me what is the meaning of this point? Yes?
So the x value 2.078 is the distance the ant has traveled, and then 0.184 is the work that it's done.
Okay, so when the ant has gone a distance of 2.078, the work done is 0.184 joules. Agree?
Well, is it the for the distance, or is it the like distance from the starting point?
Yeah, so she's asking, is it the distance traveled by the ant, or is it the horizontal distance of the ant? We did. Remember we turned it as work as a function of what? X, right? And what did that mean? Was that the distance the ant had traveled? Total distance it traveled? Okay, this is the horizontal coordinate. Horizontal distance. Or x coordinate on this graph. So after it traveled 2.078 meters, did it accomplish this much work? So should I be looking for 2 meters along here? I should be looking at? Yeah, so like here, just a little bit above 2 meters on the x-axis. And that takes me, just eyeballing, maybe to this point right here. So, no, it's not. Because it's not just the integral of f, right? It's integral of something different than f. Okay, so at this point, has the ant traveled 2.087 meters? 2.078 meters? More or less? Way more, right? Because it's by the time it gets to an x position or horizontal position of 2.078, it's covered all this distance, which is a lot more. It's like if we took that and stretched it out on the x-axis. So this is important because we got to know these numbers. I'm very glad that that was your answer because I think most of the people in the room had that same answer, okay? This is the accomplished work along the curve for whatever distance the ant traveled at the point when its x position or x coordinate horizontal position was 2.078. So it's this right here. So this point corresponds to this point. So how can we find the distance the ant has traveled at x equals 2.078? Say we want to know that. Mark.
Arc length?
Arc length. So what should I do? I want to know that. I want to know now when the ant has accomplished this much work, 1.84, how far has it traveled? What should I do? You said arc length, right?
Yeah.
So
Okay.
what is arc length?
Trying to think of like the right. So
S
of
of
a comma x.
excellent, good start.
Then
Equals
equals the integral from a to x
nice.
of I'm trying to think of how it's the square root of 1 plus
Square
f
root.
of x squared.
I think we already did that for this, right? So I'm just going to copy and paste this in our rate function up here.
Then like make them t's instead of x's.
Right. So now in the integral I need t.
Yeah.
So here I'm bypassing the arc length rate function, just going right to it. And then what should I put in?
From 0 to 2.078.
And we're expecting something a little bigger than 2, a lot bigger than 2? Yeah, a lot bigger than 2. 6 something. So when the ant has reached an x coordinate of 2.078, it's traveled 6.11 or something meters, and then the accomplished work that the ant has done along those 6.11 meters is the 0.184. Okay, doesn't make sense. All right, so we want to do the most general case. So what was still in this scenario, what was still kind of made it easy or a little too special? The force, constant force. So now we want to look at a more general case where the force can change too. And so that now the force is, read that, same path, but 0.03 times s plus 1. So depending on how far the ant has gone, that's s, the force will be variable. And so what will the force do? As the ant goes further, the force does what? Increases, right? It's going to be 0.03 times s plus 1. When s is 0, it's going to be that constant force of 0.03, but then as soon as the ant starts to move, the force starts going up. So maybe the seed is like collecting dust or some kind of residue on the ground or something, and so it's making it more difficult for the ant to push. The ant has to push with more force as it goes, continuously more force to get it to move. Okay? So how are we going to do this? So what do we have now? We have the force as a function of s. But if we're going to put it into this, what do we want our independent variable to be? X, right? So what we need is force as a function of x. So what can I do to our force function? So the force itself is a function of x. What can I do? So it has to do with s. How can we do this? Yeah.
Transform S into terms of X by using arc length.
Yeah, we know what s is, right? What is s?
The arc length.
The arc length, right? So we can use what? We can use our arc length function. That gives us values of s, right? As a function of x, right? So now this function takes x, it gives the arc length, and then the arc length in this function, capital F, then will give us the force corresponding to that value of x. So this is a composite function. Remember those? Composite function. Because the capital F function is in terms of s, we're going to use our s, that's a function of x, and kind of insert it right there. Because that's what it is. And then once we do that composition of those two functions, then our initial variable is x, and then our dependent variable is the f. That's what we want. Okay, but remember what the rate is. So the rate, so this is going to be rate 2 now. The rate is going to be force, but that force needs to be what? Transformed how? Just like we did before. So we got our force, but that's not all of the rate, right? And then we need that square root term as well to take that force along s, because that's still force along s, even though it's written in terms of variable x. It's still force along s, and then we need to get that transformed to in terms of the x variable. So we still need that square root. So I think we got it. So we kind of this was good that we set up the arc length function because we're going to need it now for the second example. So I'll come up here. Oh, I guess I lost it here. So there. So we're going to have force 2 now. So I want you to take a minute and do this. So you're going to try to write these functions. Force 2, and then rate 2, and then work 2. So can you define those functions given we got little f there, and I've got s set up there. So what will we put in for F2? What will we put in GC for R2? And then W2. You guys give it a try. So F2. What was my independent variable for F2? What goes into... So overall, that argument is what quantity? What is that given the force function? Is that quantity S or X? S. It's S, right? And that's the function we were given. Is that the function? Is that what it was? Yeah. So this is kind of the beauty of separating it all into all the different functions, is that every function we can write down as it is. We don't have to assemble them all in one statement. Okay. So that's the F2 function. And so now the rate. What did we say about the rate? So yeah. So now the rate is in terms of x, and if we use the force function. We want to use F2, right? Now what is, if it's the rate 2 is a function of x, then what needs to go inside the parentheses? S, A, right. So we got it. So from the S function, right? So these values of distance of, we're getting the force as a function of distance along, and so that's going to have to come from the S function. So we can do 0, comma x here. Is that it? Are we done with the rate function? Nope. Then we need this thing, right? So now that force is a function of S, but we've got it written in X. And now that force along the path is now transformed to the X coordinate. That's what the square root does. So with what the work you did before I started, anyone do this right so far? Got this? Mostly right? Okay, now so if we got the right rate function, then this is the easiest part, right? All we have to do is, right? Integral from A to x of r sub 2 t dt. Turn it off. Okay, so here's our original graph. So what about, I haven't turned it on yet. No, I haven't even written the statement yet. So I need to start. I'm going to redo this, but what? For W2. Okay, so there's the original. I'm about to turn on W2, so let's talk about that. What do we expect for... No, it's okay, it's stopped. All right, so what do we expect then for graphing W2 compared to W1? A lot steeper?
Yeah.
Because?
Because we're multiplying by an ever-changing constant that's increasing.
Okay. So will it still start at 0, 0?
Yeah.
Will it still always be increasing?
Yes.
Okay, so just while we're talking about that, work can decrease. So this is what would have to happen. The seed would have to morph into some creature and push back on the ant. If it starts pushing the ant backwards on the path, now we've got negative work. Okay? We know that's not happening, but that is possible, right? So you can have negative work if you get pushed back on and you go in, and you're getting pushed in the opposite direction. That's negative work, but we don't have that. So it's always going to increase. Is it going to increase linearly? Nope, it's still going to be our wiggle. And then the y coordinates of our new work function, how do they compare to the y coordinates of the old one? If you thought every point, if you compared every point's y coordinate or accomplished work of W1 and W2, how would they compare?
Bigger by a factor of the factor of the force which would be.
Yeah, so I just mean like where on the graph, right? So where will these points plot for W2 versus W1? Above, right? Okay, so watch, ready? W1 plots instantly, but
You could say graphing calculator doing a lot of work.
yep. Why is yep? So why is it taking it so long? Why is it so much work? It's doing a lot of work. That's true.
Because it has two open-ended functions.
Why is it taking? Why is it going so slow? Because who knows why it's taking so long? Yeah.
Because it's in open form, it's not in closed.
Okay, but this was the work one was in open form too, and that one graphed instantaneously. So yes, it has to do with open form. Yeah. So how did we get the rate 2 for the second one? It was based on. It was based on the what? The arc length function, and that arc length function is another open form. So we've got. In order to calculate the force, it needed to use the open form arc length, and then that gave us the rate, and then the work was based on that rate in open form also. Okay, so I'm going to pick a point right here, and you're going to take your Canvas quiz based on that point, maybe?
Yes.